now that we have determined how to convert from x's, y's, and z's, or rectangular form into cylindrical form or spherical form, we're now going to be able to modify triple integrals that are already in rectangular form to an easier form if we convert it into cylindrical or spherical. So remember that in order to evaluate a triple integral with rectangular coordinates, we essentially were integrating the quantity of dv. So you might recall that when we were calculating a triple integral over some region D in this particular case, see it's called D right here. Okay, so let's say that we were finding the volume of this, okay, then we were integrating dv, okay, or rather the change in the volume. And in this particular case, the change in the volume was just looking at this cube right here and calculating the volume of each one of these separate cubes. So if we wanted to calculate the volume, then we just took the change in x times the change in y times the change in z. And that is how we evaluated the triple integral x, y, and z. Well, we want to come up with a way to find that dv for a cylindrical coordinates as well. And the way that we're going to do that, though, with cylindrical coordinates is that now the wedges are not going to be these cubes. They're actually going to be these pieces of a cylinder. So you can see that here is a cylinder that came all the way around. Here's another cylinder that came all the way around, right? And so on. And what we're left with here is just a wedge of that cylinder. Now, it seems like it would just be length times width times height, and in a way, it kind of is, except for the fact that you can see that this is curved. This is curved. And so notice that if that's curved, then this is curved, and this is curved, and this is curved, and it's not obviously going to be just the change in x times the change in y times the change in z. So a couple of things to recognize here is we are going to calculate what this length is, and what this length is, and what this length is. And when we make each of those wedges infinitesimally small, and we fill our volume with those teeny little wedges, then what we're doing is taking the triple sum of the length times the width times the height. Now, one thing to recognize that's pretty simple here is that this quantity is obviously just the change in z. Okay, that's pretty simple to recognize. Now, if I were to extend, let's say, from the origin out to, in this xy plane, the origin out to this location here, then that would be considered r. Right? But that's not the piece of the wedge that we're interested in. We're interested in the extra change in the r direction. Okay, so that change in r is now going to be another length that we have to multiply. So far we could see that in this case, dv is going to be equal to the change in r, we'll call it dr as it gets infinitesimally small, times dz, okay? But now what we've got to do is find out what this length is right here. And the way that I've done that is that I have created just in 2 dimensions this wedge right here, this yellow little sector, okay? And so what we want to be able to recognize here is that if I was to look at this as the sector, the yellow sector that I've drawn up here in this 2-dimensional plane here, we should recognize that this is our theta. And this quantity right here is r. And we should recognize that this piece on the outside of the circle is the arc length. And the arc length, which we refer to as s, is always equal to the radius times the angle. Okay, well now if we were to look at it here in terms of this wedge, it's really the same general idea. It's just that now that r is still going to be r, But now theta is the change in theta. So this piece right here is simply going to be r times delta theta. So therefore, the volume is simply going to be r times dr times d theta times dz. And therefore, you should see the difference between the volume, or the dV, that we're going to be calculating for a triple integral and cylindrical compared to the dV that we're calculating with respect to rectangular. So what does this show us? It basically is just saying that if you have dx, dy, dz in a standard triple integral, that you could convert dx, dy, dz into dr, d theta, dz as long as you tack on an extra factor of r. And this shouldn't be too surprising, because this is exactly what we noticed when we were calculating double integrals in polar form. So all we've done at this point is we've changed our dx, dy into r dr, d theta. So now let's take a look at what this would look like in terms of spherical. Okay, so we're still going to be calculating triple integrals the same way we did in rectangular. The only difference is we're converting to r's, thetas, and z's, and we just have to multiply by an additional factor of r. Let me make that nice and bold so you can see that this is really important. We can't just convert dx, dy, and dz. We have to tack on an extra factor of r. Well, now for spherical. Spherical is a bit interesting as well, because what we're going to notice with a sphere, let's just take a look at kind of this purple piece of the sphere right here. Okay, what we're going to notice is that starting at the origin, that this region here has traveled through an angle of theta, which implies that this piece right here would be delta theta. And so if this is delta theta, this right here is delta theta. Okay. We should also recognize that extending from the origin out to the edge of the sphere is rho. And phi is extending from the z-axis downwards to the ray that rho is in. So what we're going to be seeing at this point is that as we start to use different wedges this time, spherical wedges are going to be a little bit different, because you're now going to realize that this is not a cube. This pink thing right here is not a cube. It's going to have a certain length and a certain width and a certain height. But notice that they're not going to be perpendicular to each other, and therefore they're not going to be dx, dy, dz anymore. So one thing to recognize here is that as you get out to the edge of this sphere right here, and you go a little further in that direction, then what this little piece right here is going to be is simply the change in rho. So we've got the change in rho is going to be this piece. We've got the change in theta is going to be right here. Okay. But now we've got to actually find out what the other edges are going to be. So I'd like to take a look at what the length of this blue piece is right here. Okay. So one thing to recognize is that it is an arc length, because I see that it's the outside edge of that little sector. And so we've just got to determine what is this length right here. Well, that right there is nothing more than just the r value in the xy plane. That's this piece right out here. It's just that I mapped it up onto the z-axis somewhere. And so this piece right here is simply r. But r isn't in spherical coordinates, so we just have to remember that r is equal to rho sine phi. So there's actually a line up here, so we'll write it up here. that this is equal to rho sine phi. And that's simply because of the fact that it's r. So what is this, again, this outside blue wedge? Well, keep in mind that the arc length is always equal to r times theta, r theta. Theta is right here. It's the change in theta. And so notice that that theta is nothing more than just the value of r times theta. And so that means that this wedge right here is equal to r theta, which is rho sine phi times the change in theta. And that's just because of the fact that it's the formula r theta. Okay, so we've got two pieces then. So we've got this pink edge. We also have the blue edge. The one edge that we don't have is this edge right here. So again, if we still think about this in terms of approximating it with length times width times height, and then recognizing that for infinitesimally small wedges, those are each going to go to 0, we just need to figure out what that height is. Okay. Well, now what you've got to recognize that might be a little trickier to see is that this wedge right here is also another arc length. It's the arc length extending out from the origin to there and out from the origin to there. So it's actually going to be an arc length of this wedge right here. Okay. Well, one thing to recognize about that wedge is that the radius is extending outwards to the edge of the sphere. So that radius is rho. I also know that that radius, maybe I should draw this out here. Okay. I also see that this is going to be rho times the change in the angle, but notice that the change in this angle is the change in phi because it's extending from the z-axis downwards. So this is going to be rho times the change in phi. And so I think that we're ready now to create our dv for spherical. Our dv in spherical coordinates is going to be, well, d rho is going to be one of those components times rho times the change in phi. That's going to be the other component times rho sine phi times the change in theta. Rho sine phi times the change in theta. But if we were to write all of those together here, then that would mean that I have rho squared sine phi d rho d phi d rho d phi d theta. And notice that I could rearrange the d rho d phi d theta in whatever order I choose. But one thing to recognize that's important about this is that this extra multiplier is similar to how r acted in cylindrical form. So we refer to that as the Jacobian of this triple integral. The Jacobian is just an extra multiplier that needs to be there in order to convert from one form to another. So just to sum up what we see here, dv could be written as simply dx dy dz. Or any order, dy dz dx and so on. But if I was going to convert that rectangular into polar form and say dr d theta dz, then I can't do that unless I have my extra multiplier of r, which is referred to as our Jacobian. And now after this proof, this geometric proof down here, if I wanted to convert this again into d rho, d phi, d theta, or d theta, d phi, or whatever order, you can do that as long as you remember to have the extra multiplier of rho squared sine phi. So notice that the multiplier here is just 1 for rectangular, but if we were going to convert it into one of these other two common forms, there has to be this other multiplier, and we refer to those, these two multipliers here, is called the Jacobian. We're going to see that the Jacobian of an integral doesn't always have to be either r or rho squared sine phi. These are just a couple of common substitutions that we make that are kind of easy for us to visualize in 3 dimensions, but also gives us an opportunity to convert it to make our triple integral easier to calculate. So let's do a couple examples. So before beginning this next example, we'd like to generalize triple integrals in the 3 different forms now. So if you're given a function of x, y, and z that you want to integrate, then in order to be able to do so, you're going to need to, in order to be able to do so in other coordinate systems, you're going to have to first change the variables of our function, in this case x, y, and z, into r, theta, and z. Or likewise, change them into rhos, phis, and thetas. But in addition to that, when you end up recognizing that this dx, dy, dz is our dv, you now need to recognize that to compare or to convert the x's, y's, and z's into this form, you need the extra Jacobian, and also over here, you need the extra Jacobian. So the Jacobian is just an extra multiplier that allows you to convert from one form to another. So let's set up a triple integral in cylindrical coordinates for integrating f of x, y, z, which is x times y times z, over this region that's bounded by z equals 0. Well, keep in mind that's just the xy plane. All right, this is a plane. X squared plus y minus 1 quantity squared equals 1. You should realize that in the xy plane, that's a cylinder. So in 3 dimensions, this is just a circular cylinder, which is why turning it into cylindrical form can be beneficial. And lastly, z equals x squared plus y squared. Well, that's a paraboloid. Paraboloid here. Okay, so now we just want to think about what's going on here. If we take a look at the xy trace, just to kind of see what this would look like in the xy direction, okay, then we see that it's nothing more than just a circle that's centered at the point 0, 1. Centered at the point 0, 1 right here. And it has a radius of 1, so that means it's going to extend upwards to 2, downwards to 0, and then right and left 1 unit as well. Okay. So this right here is our xy trace. That's a bad circle. Let's try that again. Okay. So remember that it can help to actually have traces when you're trying to come up with a triple integral. So if this right here is our xy trace, it's often helpful in cylindrical form to always have your z first, even though you don't need to. It can help to have z first, and then your r and theta come second. And the reason is that most of our curves are going to be in terms of z equals, and so having those z coordinates there is going to be beneficial. So let's set those up. Let's set up the fact that we have our z's, then our r's, then our thetas. So first of all, this is multiplying x times y times z times r dz dr d theta. Now, even though you could rearrange the order, this is typically the order in which you want them, mainly because thetas, you always want those to be constant values. Z, those are the functions, the surfaces that are going to be bounding this region on both the bottom and the top. And typically r is going to be a function of theta. And so this is normally the order in which you want things to be, all right? Now, one thing to recognize here is that if z is the innermost region, then z must be referring to these values, and r is referring to these values, and theta is referring out to these values. Okay, well, let's think about what's going on here. Z equals 0 is the xy plane, so it's bounded on the bottom by the xy plane, and it's bounded on the top by z equals x squared plus y squared. Okay, so that's pretty straightforward then, because that must mean that we already have what our z coordinates are going to be. It's going to extend from z equals 0 up to z equals x squared plus y squared. Now you might be recognizing we don't have everything in terms of r's and thetas yet, but that's okay. We can convert in a few minutes here. So now we know that these are going to have to be r values, and these will have to be theta values. Okay, so now we've got to think about this region in the xy plane. Since the last two limits of integration are in terms of r's and thetas, then that just means that I have to convert this equation in the xy plane to an equation involving r's and thetas. So when we do so, we're just going to have r cosine theta squared plus y, which is r sine theta, minus 1 squared is equal to 1. Now this is fine, except for the fact that we typically want to have r equals a function of theta. So let's just expand this a little bit and get r squared cosine squared theta. Now if we expand this, we get r squared sine squared theta minus 2r sine theta plus 1 equals 1. Well, notice for this piece right here, when I factor out an r squared, I'm left with cosine squared theta plus sine squared theta, which is why all we're left with here is r squared minus 2r sine theta. And if I subtract this 1 from both sides, then I'm simply left with equals 0. So now that means that if I factor out an r, I get r minus 2 sine theta. And by the zero product property, that means that either r is equal to 0 or r is equal to 2 sine theta. Now let's think about what that implies. That means that either r is 0, which means the origin, or r is going to end, depending on what the angle is, at this orange circle. So notice that as I rotate around, I'm eventually going to hit every single one of these points on this circle. And so this circle is referred to as the circle r equals 2 sine theta. So what that tells me as well is that for my second limits of integration, r is going to extend from 0 out to 2 sine theta. But now we've got to recognize as well that the angle, you often think of it as just being 0 to 2 pi, but don't just jump to the conclusion that it's always 0 to 2 pi. We just want to find out from this figure here, when do we finally get back to where we began? Okay, so essentially one way you can look at this is just geometrically, okay, by saying that as I rotate from r equals 0, which is an angle of 0, and I keep rotating around here, notice that I'm hitting every single value by the time I get to pi. not by the time I end up getting to 2 pi. So that must mean that if this is the angle of 0 and this is the angle of pi, then I know that my region is going to be from 0 to pi. Another way to do this is to think about this being 0. When do I get back to r equals 0 again? Well, I get back to r equals 0 when sine of theta equals 0. And sine of theta is equal to 0 at the theta values of 0 and pi, and 2 pi. But in this case, we can see that we've hit all of our values here by the time I go from 0 up to pi. Now I'm close to being done, but there's a couple of things that are an issue. One issue here is that x squared plus y squared doesn't have r's and thetas. And likewise, the function that I'm integrating is still in terms of x's, y's, and z's. So I've got to start combining these together or simplifying this. So this becomes the integral from 0 to pi, and that's going to be d theta, of the integral from 0 to 2 sine theta, and that's going to be my dr, and from z equals 0 up to x squared plus y squared. Now think about this. X squared plus y squared in polar form is r squared. So now I've got all of my limits of integration are now in cylindrical coordinates, and that's going to be dz. Now one thing not to forget here is that I've got to multiply by r just automatically. But then the last thing I need to know is how to convert x, y, and z into r's, thetas, and z's. Well, x, remember, is r cosine theta. Y is r sine theta. And z is just z. So now looking at that integral, everything is in terms of r's, thetas, and z's. And the last step is just to simplify everything that's in the integrand so that it becomes a much more integrable form. So r cubed cosine theta sine theta times z. And so now I'm just integrating with respect to z first, then I'll integrate with respect to r next, then I'll integrate with respect to theta, and that should give me my final result. So let's look at an example in terms of spherical coordinates. Well, in order to set up a triple integral to find this particular volume, okay, we first of all are going to want to make sure that we have our correct order. Okay, so it doesn't matter technically, as I mentioned before, the order, but in general, you're going to be given equations in polar form in terms of rho. Okay, so that's why rho should be the innermost, and then you could go whatever order you want from there because phi and theta will always be constant. Okay, it'll be a constant phi and a constant theta. So in this case, we'll just go rho, then phi, then theta. Now keep in mind that if I'm going to find a volume, we also need to make sure that we have the appropriate Jacobian, which is rho squared sine phi, just automatically. And since we're just integrating to find a volume, then the function f of rho phi theta is really just 1. We're finding the volume, so we're just integrating 1 dv. So now that means that we need to fill in our rho values here. And then we need to fill in our phis. And we need to fill in our thetas. Now, like I said, we could have interchanged theta and phi if we chose to, but we're just going to keep it as is here. Okay, so now we need to think about what this is saying. It's saying that it's bounded below, this region is bounded below by the hemisphere rho equals 1, z greater than or equal to 0. Well, a hemisphere is just a portion of a sphere. Rho equals 1 is a sphere, but we're saying that the sphere needs to be purely above the xy plane, which is why I know that the lowest rho value is going to be rho equals 1, since it says it's bounded below by that hemisphere. And it's bounded above by the cardioid of revolution, You don't need to know the name necessarily. That's what it's called. It's 1 plus cosine of phi. Okay. Now we can see in another way why we know that 1 plus cosine phi is going to be the top one, but we'll do that in a second here. Let's go to our phi values. Now keep in mind that when you're dealing with cylindrical or with spherical coordinates start with a phi value at the z-axis going downwards. So the values for phi can be anywhere between 0 and pi. Okay, 0 is at the positive z-axis, pi is at the negative z-axis, and pi over 2 is if it touches the xy plane or if it hits the xy plane. Well, considering the xy plane is the lowest part of this region, then I know that phi is going to extend from 0, which is the z-axis, to pi over 2, which is the xy plane. And now I have to realize, how does theta change? Okay, well, unless otherwise stipulated, since this is a full hemisphere, theta will extend from 0 all the way through a full rotation, which would take me to 2 pi. Now, one reason to know, or one way to know that this is going to be cosine of phi is going to be on top, is that this quantity here, okay, this 1 plus cosine phi, from 0 to pi over 2, it's always going to be bigger than 1. If theta, or if phi is pi over 2, cosine of pi over 2 is 0, so that's going to give me a rho value of 1. But if phi is anywhere between 0 and pi over 2, then cosine of phi will be a number between 0 and 1. And if I add 1, that'll be larger than 1. So that's why 1 would be on the bottom, and this would be the larger value on top. So now I've set up the triple integral, and now it's just a matter of integrating. Okay, just realize that these are acting just like x's, y's, and z's. We just have to integrate in this similar fashion. So the first thing we're doing is this first integral. So integrating with respect to rho gives me 1/3 rho cubed, because rho is the variable, and sine phi just follows along. Now we know we're integrating that from 1 to 1 plus cosine phi. Okay, so now we just have to plug those quantities in, and that's going to give me 1/3 times 1 plus cosine phi cubed times sine phi minus, and now I plug in 1 for rho, and I get 1/3 sine phi. Okay, and so now that gives me a function of phi, which I now am going to be able to integrate again with respect to phi in the next step. Now we're going to continue with the second integral, which is now going to be in terms of phi. So remember, phi is the variable, theta is a constant. So if we integrate this with respect to phi, then let's think what happens here. So u could be thought of as this little piece right here. Let's just do a little u substitution. Well, if I let that quantity be u, then the derivative is negative sine theta. So this right here is just negative du. So all I'm integrating is negative 1/3 u cubed. So that becomes negative 1/12 u to the 4th, which is 1 plus cosine phi to the power of 4. So that takes care of the first term. Now the integral of 1/3 sine theta is just simply 1/3 cosine theta, so plus 1/3 cosine theta. Because remember, the integral of sine theta is negative cosine theta. Oh, I'm sorry, that's not theta, it is phi, cosine of phi. And that is evaluated from phi equals 0 up to phi equals pi over 2. Okay. Well, now we just plug in pi over 2 and plug in 0 to each of these and see what happens. So cosine of pi over 2, that's going to give 0. So that's just simply going to be negative 1/12 times 1 to the 4th plus, and cosine of pi over 2 is 0, minus, and now I plug in 0, and cosine of 0 is 1. So now we're left with negative 1/12 times 2 to the 4th plus 1/3 times cosine of 0, which is 1/3 times 1. Okay. And lastly, this gives us, well, let's continue. That gives us negative 1/12 plus 16/12 plus or minus 1/3. Minus 1/3. Okay, so if I make this into 4/12, then that gives me a total of 11/12. Okay. So now we just got to realize that whatever that quantity was, we are now taking the integral from 0 to 2 pi with respect to theta. And the integral from 0 to 2 pi with respect to theta. So make sure to have that in every step along the way here. Should make sure to group these in here. And lastly, that just means that the last step here is to integrate 11/12 with respect to theta. Well, the integral of constant is just the constant times theta. So this integral right here is just 11/12 theta evaluated from 0 to 2 pi, which gives me 11 pi over 6. Or rather, I guess we could plug in and we get 22 pi over 12 minus 0, which gives me an answer of 11 pi over 6. And so notice that once you set up the integral, this would have been a much more challenging function to try to do in rectangular coordinates, simply because when I convert this into rectangular, the integral would be insane. The limits of integration would be extremely challenging. So even though we had to deal with some thetas and phis and some trigonometry, this still made our process much, much easier to deal with.